our masterclass. It's Monday, May the 15th. It's 5 p.m. in Central European time. It's 11 a.m. where David is. I'm not even sure where you're exactly based right now, but somewhere west of me, apparently.
Yeah. Toronto.
Yeah. So Toronto is 11, so we wait for some people to come in. Probably we have some people joining from even further from the west, so they probably need to make sure their breakfast coffee is well brewed. For the ones that are joining from the more eastern side of Central European time, I hope you are not yet over dinner or not yet falling asleep or just about to interrupt your favorite Netflix show for the session. We just wait for another 2-3 minutes for people to come in, and I'm really happy to see already a couple of names that I've been also seeing last Monday. So apparently we have some quantum enthusiasts amongst us, which is great, and I will guarantee you today it won't get boring. It would be quite the opposite. It will be exciting again after last week's session where we started exploring a little bit the foundations of quantum physics and what you could already do or what kind of stuff you're already using on a daily basis where quantum is already present. Now, this time we are going to look a little bit at a different subject, and this is economics. So as you probably know from last time, at least the names that are already online that have been here last time, this first couple of minutes, I'm just giving a little bit of an overview and bridging a little bit the time. If you find this boring, just feel free to put me onto silent and come back in a minute or two. Then everybody should be in here. But for the ones that enjoy this 2 minutes of bridging talk from my end, today we are talking about quantum economics, and we're doing it in a very special edition because we're doing it for absolute beginners. Because probably if you're joining the session saying, ooh, economics, I have heard about this in high school, I've heard about it at university, but I'm a little bit on the end where I forgot most of those things, but there's some names that resonate. Don't worry about it, and we will make sure that you can follow this session properly, and you don't need to have your PhD in economics to follow David's presentation here on that end. And this will be the exciting starting point for us today. So what we want to also achieve with our masterclass series in the quantum space is to give you an overview of the variety of topics, that it's not only limited to quantum computers and all this fancy physics that you have heard before, but that quantum technologies and the principles or the paradigm shift that quantum is bringing us into this beautiful world has a lot of different facades and a lot of different ways of expressing its beauty. And today we are looking at one of those topics that we all know every single day, and this is economics, or more precisely, money. And with that, we see that people are slowly coming in. I would say we are wasting no more time and starting our session. So once again, welcome to our masterclass, the second edition of the Quantum Masterclass series as part of the Global Masters in Quantum Technologies for Business Transformation. Today, quantum economics for absolute beginners with our dear friend, David. David is already with us. And if you have probably Googled or searched for David upfront, you have seen probably, wow, this man has time to write books. And he writes not only books, but he writes amazing books. But he's not an author. He's actually an applied mathematician, which makes it even more interesting, right? Because everybody who has math in high school knows that math likes also letters. So it's not a big surprise that David is also writing books and is really good with bringing letters into beautiful words and compelling stories after that. And as another surprise, or not a surprise to you, he has also written a book called Quantum Economics, which is the new science of money and has received great reception all over the world. And shed some great light on not only the topic, but also what money actually is and how quantum plays into these roles. And with that, David, a warm welcome to the sessions for everybody that is joining in. If you have any questions, use the Q&A section, use the chat. We are answering all questions by the end of the session. And if you raise your hand by the end of the session and want to contribute to this discussion, feel free to do so. David, the stage for the moment is yours. Thank you so much for joining us this evening, or this morning in your case.
Thank you very much, Robin, for the introduction. It's nice to be here. So about 150 years ago, when Charles Babbage invented the first computer, which he called the analytical engine, the person who was considered the first computer programmer, Ada Lovelace, wrote about the effect that she thought this would have outside of computing. She talked about a sort of indirect and reciprocal influence on science itself. It would throw new light on subject matters, lead to new views, and even lead to something that she called the calculus of the nervous system. And it is possible to draw a link between that first computer and the so-called hedonic calculus of neoclassical economists, all the way up to our modern mainstream theory of economics with its laws of supply and demand. But now we're starting to experiment with these new quantum computers, and we're thinking in terms of quantum logic and quantum circuits. And then the question is, how is that going to change the way, what sort of new views is this likely to induce about things like the economy? So in other words, what happens if we quantize economics? Now, this does not mean emulating quantum physics. It means using quantum as a mathematical framework. Money is a form of information that does not behave like a classical object. And as Scott Aaronson wrote, quantum mathematics is about information and probabilities and observables and how they relate to each other. And this applies as well to something like the economy as it does to subatomic particles. And you've got ideas from quantum going into things like art and music and so on. So, the question is, how is this going to affect economics? So to start with sort of a little bit of an overview of quantum ideas. So in physics, the quantum revolution was born when physicists found that at the subatomic level, energy was always exchanged in terms of these discrete parcels, which they called quanta, that's from the Latin for how much. And in economics, the equivalent is financial transactions. As if you buy an ice cream in Italy, you say quanto costa, which brings the quantum connection a little closer. So money behaves in some ways like an object, but it's not a classical one. It shows signature properties of quantum systems, such as discreteness, indeterminacy, entanglement, duality, interference, and so on. Starting with the simplest of these, or the most direct one, is discreteness. Physicist Erwin Schrödinger once said, if we have to go on with these damned quantum jumps, then I'm sorry that I ever got involved. But in money, this idea of discreteness is completely sort of natural. So if you go to the store and you pay with your card, the money doesn't flow out in a continuous stream. It just jumps in a discrete manner. In physics, the position of a particle is fundamentally indeterminate and is in a sense constructed by the measurement procedure, and so it is in markets. So if you put your house up for sale, you might have a fuzzy idea of the value, but the exact price is only determined when there's an actual transaction, and that's when a number is put on the value of that house. And this is money's job. It's a way to collapse our fuzzy idea of value down to a hard number. And you can see that if you look at the design of a US dollar bill, you've got these written one and a numerical one in each corner. And you've got a $1 down at the bottom, and you've got a big one in the middle and a whole lot of ones on the other sides. They're really very insistent about this notion of number, that this is worth one. So that's what we're doing with money. And the thing is, though, that numbers are sort of incompatible with objects, the idea of value. And this leads to these interesting properties. These dual properties of money objects are reflected in the two main historical theories: Bullianism, like money is gold and nothing else, as J.P. Morgan said in 1912, and Chartalism, as Alfred Mitchell Innes said next year, credit alone is money. And then along comes Bitcoin, which on the one hand appears to be completely virtual, but on the other hand is very real, as you'll discover if you lose the hard drive on which your Bitcoins are located. So money always has these two sides to it, the virtual and the real. They're always like tied together. And it's similar to the wave particle complementarity, which is reflected in theories of light. So in physics, we kind of bounce back and forth between the idea that light is a wave, like Aristotle, or light is a stream of particles, as Newton thought. And then finally, quantum physicists found that it's both at the same time, has properties of each. And you could sort of think of this broadness a bit beyond the idea of money. I mean, just as mainstream economics treats money as an inert object, so it treats our preferences as fixed and known with some cognitive biases. There's kind of a basis of economics that we have. We go into the world with preferences for one thing, you know, for bananas over apples or vice versa. But often our preferences are made up in response to questions, which act like a kind of a measurement event. So thoughts and ideas, like money, they behave in some ways like objects, but they're not classical ones. In fact, Bohr's theory of wave particle complementarity was inspired by the observation from psychologists that we can hold opposite ideas in the mind at the same time, leading to effects like cognitive dissonance. I'm going to talk a bit about this kind of mental interference pattern later on. In physics, particles can become entangled. So they act as a single system. So, you know, electrons, which are entangled and they're opposite ends of the universe, and a measurement on one still tells you something about the other, and very mysterious. But in the financial system, we have more obvious forms of entanglement. And financial assets and virtual liabilities have quantum characteristics of entanglement with each other, not yet fully understood. So I'm going to give some examples of that later on. In mainstream economics, there's this idea of rational economic man who always makes these sort of objective decisions about everything. Quantum economic person, on the other hand, is entangled, indeterminate, dynamic, paradoxical, and alive. As Slavoj Žižek said, as a fact rarely noticed is that the propositions of quantum physics appear to defy our common sense view of material reality, but they are strangely echo another domain, sort of the human domain. It's as if in the quantum universe, the human spirit encounters itself outside itself. So again, what happens if we quantize economics? Bearing in mind that quantum mechanics could have been invented by mathematicians in the 19th century without any input from experiments. So it's like a mathematical ideas, you know. So what happens if we apply that to the economy? Well, there, you know, as soon as you start talking about this, there are a number of reasons why, you know, occurs to you like why you shouldn't do it, right? I mean, one is that, as Niels Bohr said, you know, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Richard Feynman, nobody understands quantum mechanics. John von Neumann, you don't understand quantum mechanics, you just get used to it. So it's, you know, it seems to be sort of impossible to understand. There are these weird ideas like Schrodinger's cat, which can be alive and dead at the same time. And it's common to sort of read, like from this website from a university, they talk about superposition and entanglement. And it's okay to be a bit baffled by these concepts since we don't experience them in our day-to-day lives. They're only for subatomic particles. And yet when you think about it, superposition, different ideas, entanglement with different things, they don't seem that strange. And then there's the forbidding mathematics, of course, which is like truly scary. And then also both economists and physicists don't really like, you know, the idea of kind of taking ideas from physics and transplanting them to another field like economics. So Paul Samuelson, for example, sort of said that, you know, you can't, it's just not valid to do this. And there are a bunch more reasons, and I've got a blog post on this, 10 reasons to not be quantum. Just one thing about this picture of Samuelson, there's kind of this X-shaped diagram in the background, which I'm going to come back to later. That's the classical supply and demand diagram. Okay, so there are all these, you know, very good reasons to not do this. These blockers, and I think like the way to kind of handle this is to do something sort of be very easy for some of the people in the audience, to be very hard for other people in the audience, right? which is to actually just sort of let all this stuff go about subatomic particles and so on, and weird entanglements and kind of crazy sort of ideas. Just forget physics for a while, because the economy is not physics, and if these ideas are good and valid in economics, we need to justify them because they work in economics, not because they work in physics. So it's a mathematical framework, and it's not to say that physicists obviously have a ton to offer and all this kind of thing, but in order to kind of really see where this is coming from, we just need to boil it down to something simpler to do with our own lives. And so, as an example, some of you may have seen this movie from the Coen Brothers movie from the 90s, No Country for Old Men. And there's a scene where there's a hitman played by Javier Bardem, and he goes to a gas station, and the gas station attendant has seen a little bit more than he should have. And Bardem asks him, "What's the most you ever lost on a coin toss?" And there's this moment of suspense where he tosses the coin in the air, and you don't know what's going to happen, but that this is a risky situation. He slams it down in his head, and that turns out to be good news for the gas station attendant because it means that he gets to live. But imagine that we wanted to somehow model mathematically that moment, not of the coin, but of the information about the coin. Okay, that's an important distinction. So we're talking about information. Is it heads? Is it tails? And we could do that. So there's two possibilities. So we could draw like a little axis like this, and one is heads and one's tails. And then we're sort of suspended this moment of uncertainty between these two possibilities. So we could do a 45-degree angle. And we would do that because we're going to say the probability of heads is kind of project down onto that axis, and the probability of tails is going to be this. But then we're going to square the probabilities. And the reason we want to do that is because we want them to add to 1. And then there will be, if we looked at the probability of getting heads or tails, living or dying in this case, the heads 50%, tails 50%. Okay, so this is sort of just a different kind of probability. So in classical probability, you have two options. You got heads or tails. And this quantum probability, which is sometimes called the 2 norm, you can have the superposition state where it can be heads and tails at the same time. And you just measure probabilities in a different way. So that's really what quantum is referring to here. And although that seems kind of a small change, it leads to all sorts of interesting things. So for example, I could also depict my situation here by flipping that over to the other side. And I would end up with what looks like a negative probability. The size of the probability, because I take the squares, the square of a negative number is the same as the square of the positive. So I'm still getting 50% chance heads, 50% chance tails. But I have these negative numbers appearing in my calculations. And then you can kind of think, well, if you're doing more complicated calculations, negative numbers means that probabilities might cancel out. Or I might want to take the square root of a probability. And if it's negative, I'm going to end up with complex numbers, meaning numbers that involve the square root of -1. So suddenly my classical probability has kind of become much more complicated, even though it's, the idea is very simple. And then I can think, okay, what happens if I have 2 coins? So if I had 2 coins, I would have one coin can be heads and tails, and the other one can be heads or tails. And if each of them had a equal probability, then the chances of getting one being heads, the other being heads would be 25%, the first being heads, the second be tails, 25%, and so on for the 4 possibilities. But I could also have, in quantum probability, I can say that these things are entangled. So it's just it's like a rule which I impose on. And I say, well, if one is heads, the other has to be heads. And then I have a 50% chance of heads, and 50% chance of tails. And that's what entanglement means in this case. So it's like a rule. And then if you start thinking, okay, I got 2 coins, 2 possibilities for each one, if I wanted to I can depict one coin on a 2-dimensional graph. In order to depict both coins, all the possibilities, I would need a 4-dimensional graph, which is, kind of tricky. And if I would add 50 coins, I would need 2 to the power of 50 dimensions. So it's about a quadrillion dimensions. And this is where the power of quantum computing comes from. And quantum computers take advantage of entanglement and interference to perform their calculations. Okay, so if we kind of looked inside a quantum computer and we ask, okay, what's actually going on? You know, we're going to replace our little coin toss thing with a qubit. So a qubit is sort of like a quantum coin, if you like. And instead of heads and tails, we're going to call it 0 and 1. So 0 is horizontal in this case, and 1 is going to be vertical. So I initialize my circuit as 0, then I'm going to rotate these qubits, so rotate them to different angles. Then I do entanglement. So entanglement is something where you link these two things, and here I'm using something called a controlled NOT gate, a C NOT gate, which flips the lower qubit depending on the state of the upper control qubit. And then at the end I measure, and if I do this lots of times, I have to do it probabilistically, and then I just kind of collate my outcomes, which can be 0 for the first qubit, 0 for the second one, 0, 1, 1, 0, 1, 1, and so on. So what is that control NOT gate doing? Well, what it does is sort of like a quantum version of a if-then statement, if you're familiar with classical computing. So if the top qubit is 1, so that's the vertical, then the bottom qubit gets flipped. So 1 goes to 0, 0 goes to 1. If, on the other hand, the top qubit is 0, then the bottom qubit remains unchanged. So that is that's sort of like a basic quantum circuit. The thing you've got to remember here is that I'm saying if the top qubit is 1. What that really means is that the top qubit is superposed. Is part of it 0, part of it's 1. So the part of it, which is 1, flips the bottom qubit. And so, actually kind of like working out the math behind this can be pretty complicated. Let's just look at a really simple example of an application, okay? So here's one, early form of money called tally sticks. So it's over 1,000 years old, about 1,000 years old, and they've got what they were is like wooden sticks, so about 10 sort of foot long, and they were notched to indicate the worth, so pound, shilling, pence, depending on the thickness of the notches. And then they were cut down the middle, and one half was kept by the creditor, who would be like the sovereign, and the other half was handed to the debtor, who owed money. And then when the debt was repaid, the two sides were matched and destroyed. And at first, these were primarily used for tax collection, but they soon became a general form of money. And the reason was that the stock, which is the part that the creditor has, it represents the right to collect a debt. So it had a well-defined value. It meant, if the value of if it was a debt of 10 pounds, then that thing was worth 10 pounds. You could use it, go collect that debt. So it could be traded or used to pay taxes. So how could we, as a sort of exercise, how could we do this using our fancy quantum circuit? Well, we have two qubits. So one's going to represent the debtor up at the top here, and we're going to rotate his qubit like this. And we have to assign a meaning to this. So if the qubit is vertical, that means he's going to pay the debt. If it's horizontal, it means he's not going to. And the fact that the angle is nearly vertical means he's probably going to pay the debt. The sovereign, we rotate his qubit up to 90 degrees, which means he is not going to get paid. But we then do this entanglement, which is the contract, the tally stick. And this is what sort of imposes these entanglement rules on this. So it means that, so again, if the top qubit is 1, then the bottom qubit gets flipped to 0, and so on. And then we just look at the probability. So you kind of go through and you say, well, you follow the logic and you say, there's the debtor, the most likely outcome is that the debtor does not default and the creditor does collect, and there's a 95% chance of that. There's also a 5% probability that the debtor defaults and the sovereign does not collect, but there's 0 probability that, for example, the debtor can default and the creditor can collect, because that doesn't work that way. So there's only 2 possibilities. And so this form of money, so it might seem like tally sticks are a bit outmoded, but in fact, actually, that's exactly how money creation really works. So most modern economies, the vast majority of money is created by banks, private banks lending for things like mortgages on houses. And as central bankers have said, the way this works is, they don't borrow that money. The money lent to you by the bank has been created by the bank itself out of nothing, which seems sort of defy classical logic in a way. And what it is exactly the same thing as the tally stick. So you have a debtor who takes out a mortgage on a house, and they go to the bank, their local neighborhood bank, whatever that is, and then there's a mortgage contract which entangles it, and then out at the end you get money printed. And then it's interesting, like if you track this money creation process with the house price index, they tend to go up together, which this is actually a driving force in the real economy. Okay, so that, obviously that seems like you don't need a fancy quantum computer, right? Just to sort of model how money is created. But the reason we want to do it is that the debt circuit is quantum because the value of the debt depends on the debtor who is being modeled as being in the superposed undecided state. So neoclassical economics assumes approximately rational behavior, but just as the value of the tally depends on the subjective mental state of the debtor, so-called objective decisions depend on the subjective context. And it turns out that exactly the same quantum circuit can be used to model a range of cognitive phenomena that elude classical treatment, such as the order effect, where responses depend on question order, preference reversal, where we change our mind depending on the context, mental interference, such as cognitive dissonance, and cooperation and altruism, as in The Prisoner's Dilemma. So just talk about a couple of these. So one is something called the disjunction effect. And so this goes back to an experiment that was performed back in the 90s by behavioral economists. And they asked the students to imagine that they have a tough exam coming up and they have an opportunity to buy a vacation to Hawaii at a very good price. Would they take the offer? So in one version, the students were told the result of the exam. So if the result was passed, then 54% chose to buy. They passed the exam, they felt good, yeah, go on holiday. If the result was fail, then 57% chose to buy. Maybe the reason here is that they feel they need to be cheered up, by going on holiday. But they're both around the same, and 55.5% is the average, so it's rounded up to 56%. But then in another version, they're told they will not know the result. And so now you've got these two reasons for kind of, doing, for taking the vacation, buying the vacation, but they interfere in the mind. And you only get, the probability is only 32% chose to buy. So this defies classical logic, because classical logic, the answer should be the average is 56%. If you do classical logic. And so actually, in order to do this in a consistent way, you want to do the quantum circuit. So we have this entanglement thing. We start off at 0. This is our test result over here. We got a 45-degree angle, so 50% chance of passing or failing. And then we have to sort of tune our qubit for our rotation for the second qubit. And then we can do that so that when we measure it at the end, we get the kind of outcomes that would agree for that sort of interference thing. So it's kind of, so this is more complicated than the money creation circuit in a way, but it's exactly the same idea. What it is like the context here, our upper qubit, is shaping the decision through this controlled NOT gate. And we can generalize this to any decision B, which is shaped by a subjective context A. And if we estimate the magnitude of that interference term, so we sort of say, okay, what happens if this is sort of our subjective thing? And the first one, it was how we feel about passing or failing a test, which actually has nothing to do really with the vacation, but it changes the context. How does that affect our decision? And you can sort of estimate it just by looking at all the sort of averaging over the various different possibilities, and you find that it influences the decision by about plus or minus 25%. And a corollary of that is something called the preference reversal criterion, which is that objective factors need to increase by a factor 3 to switch from a subjectively attractive option to a subjectively unattractive option. So this is interesting because it's sort of saying there's this huge role for subjective context, which doesn't appear in kind of neoclassical, thinking. So, and this is something we're all familiar with. So, for example, if you have, let's say there's some person just likes a particular politician for whatever reason, and you're sort of arguing, trying to change their mind using rational, arguments, it's very, very hard to do that, to sort of overcome that subjective appeal. As a kind of real world application of this is preference reversal during the US housing crisis. So following the US housing crisis of 2007 and 8 and 9, that time, so you had millions of US homeowners could have saved tons of money by strategically defaulting on their mortgages because the value of their house had fallen below the value of their mortgage. And if surveys showed, so if you went around and asked people kind of, okay, what would you do under this circumstance theoretically, it was shown that people were ready to default on their mortgages when the context was a survey. When they were actually faced with a real decision, the median borrower only defaulted when they were 62% underwater. So they had to be like way underwater before they would consider defaulting on their mortgage. And this, again, this doesn't make sense when you sort of think about classical logic, because, if they wanted to optimize their utility or whatever, they should have solved it. But this subjective feeling of, things like, like fear of what would happen, shame about defaulting on their mortgage and so on, overcame all this kind of rational arguments. And this was not a small effect. It would have cost estimated $750 billion to restore all those underwater borrowers. Another game, if people have studied economics, they might have come across the prisoner's dilemma, which is this thing where you have two prisoners and their sentences depend on whether they cooperate with each other or whether one sort of betrays the other one. And according to neoclassical economics or neoclassical theory, people should betray each other because it optimizes their possibility. In practice, people tend to cooperate more. They show altruism. And again, this is something, and actually people are developing quantum models of games such as Prisoner's Dilemma, exactly because they are more easily modeled using the quantum formalism. Okay, sort of summarize then, you kind of think, well, with neoclassical economics, you've got the context of a decision. So this can represent a preceding event, beliefs about another person, any subjective factor. It just kind of go anywhere. It doesn't matter because the rational decision is sovereign. In quantum economics, on the other hand, these things are coupled. So the context and affects the final decision. And I've overlaid this with the two hemispheres of the brain, as James McGilchrist, a psychologist, has said that the right hemisphere sees each thing in its context, or associated with context, while the left side of the brain is associated with the rational decision-making component. And so in our actual, when we're thinking about problems, this sort of incompatibility between these concepts and different aspects of the problem can lead to mental interference effects. But on the other hand, it can also lead to creative solutions, as in the aha moment, which is considered to be a right brain phenomenon. And you might sort of start thinking, okay, well, we've got a little circuit for one person's decision making. What happens if that person's decision forms part of the context for another person's decision? And what sort of thing is that going to lead to? And then you could imagine a circuit where you put loads of these. So this is our basic entanglement circuit here. Sort of string lots of these things together in different ways. What would that be? Is it a quantum agent-based simulation of a market? Well, actually, this is a circuit for quantum artificial intelligence. It's used for simulating financial time series. So it's interesting to see how these this link really between the work which has been done in quantum cognition kind of reappearing in quantum artificial intelligence. Okay, so that's I want to kind of, for the next part of the talk, just going to switch gears a little bit and talk about how quantum models can be used in a very practical way in the field of finance. And part of this is, again, kind of comparing the quantum approach with the classical approach. So in the classical models of the economy or the financial system, something like a stock market, the basic idea is that markets are supposed to be at equilibrium in a sense, which means that, so you have this idea of efficient markets. People may have heard of the efficient market hypothesis. It's this idea of kind of perfect information, everything is priced more or less correctly. You have this kind of static equilibrium. There's no real sense of dynamics, forces, change, or time. It's a bit like Aristotelian physics, where everything finds its level immediately in a vacuum. And the changes in price follow this log normal distribution. So it's like the old bell curve idea. But then if you sort of think, okay, well, actually, we don't buy that. We don't think markets are equilibrium. We need to consider dynamics. So one way to do that is to say, well, take this normal distribution, and we can view it as a kind of sort of a trick from sort of think about how our probability is like this bell-shaped thing. You can think of a kind of a force which is corralling that probability in. So if there was no kind of ordering force on this, the probability would kind of, let's say, sort of spread out and like that. But there's a sort of a force, a kind of like a spring-like force, which is corralling this decision in. So you can kind of think of something which is making the market price, kind of attracting it to that central point, but there's still sort of dynamics. But then you end up with a kind of a spring-like force, and we know that markets don't behave like springs. Let's apply quantum probability to this and see what happens. Well, the quantum version of a spring is a quantum harmonic oscillator, which has all sorts of interesting things. So it's a bit like, if this is your normal distribution from classical probability, the question is, how do you make that dynamic? And in the quantum version, what happens is it spins around like this. And the reason is, this is we're using imaginary numbers here. So it's like in the imaginary plane. But it's kind of a way of creating this interesting mathematical object, which has a dynamic component to it, but has aspects which are similar to that normal distribution. So basically this thing is spinning around like that. So that's why I got that little person skipping the rope. And the speed at which it's spinning is going to measure the average rate of turnover. The energy level, the degree of energy represented by this ball, corresponds to the number of transactions in the current time step. And then an interesting thing about this harmonic oscillator is that you spin faster, it starts to distort. You get a higher energy level and it changes its shape and it starts to spread out. And how can we use this to model market? Well, one thing is to sort of say, okay, let's just use this as our model and see what kind of predictions come out of it and see how they tally with the way markets actually behave. Well, one is that because you have transactions going on in this in the market, that means you're going to get varying energy levels which follow a particular distribution. And what you find is that the price change distribution is not kind of a nice bell-shaped thing. It's kind of peak. It's got a sharper peak up here, and it's got these sort of tails, so-called fat tails, which extend out further. So it's not kind of like a nice round normal distribution. It's more kind of like peaked like that. And this is something that comes naturally out of the quantum simulation and doesn't really fit at all. So I'm going to talk about the Black-Scholes model, but like it doesn't fit with that log normal bell curve type thing. Another thing is, okay, let's say we've got this thing which is representing our price. What happens if we have a large order come in? And let's say that we have an order which is kind of 10% of the, so V here is the daily order, and we're going to do an excess order, which is like 10% of that. That will boost the price. You sort of think, okay, if you got like, if you make a really big order in a very short time, like it's going to boost the price somehow. And we can just look and we can say, and then what you find is that according to the formula, it's basically because this thing is a spring, like the way it behaves, or the way it responds is in like this kind of square root fashion. And it's a very simple thing. There's no additional parameters here. Like sigma is just the the so-called volatility, which is kind of like the width of this thing, which you can go out and measure. So it leads to that very sort of simple square root thing. So that's something that is known about markets. But the quantum model gives a very kind of a neat proof, because it doesn't have, you don't have any extra parameters being added, basically. But then the other thing to come out of it, which is that because our distribution, as I mentioned about the energy level, kind of makes it distort, you get like you can actually estimate the kind of variability of the price. And you end up getting this formula, which looks like this. And this one is interesting because it actually, you can't get that formula from the classical model, because it doesn't work in the classical perspective. And so it actually kind of contradicts papers, and yet it does fit the data very well. And then you kind of link these things. So this is our square root thing, which I just showed earlier. But then if you sort of think, okay, well, if I had a negative shock where I'm selling, and so that's going to lower the price, and I attach those together, and I end up with a curve like this. And then you kind of compare this to the sort of mainstream economics thing with this. You got supply line, and everyone will have seen this if they've ever taken an economics course, at least, and demand. These are like two fixed lines, and they intersect at this sort of equilibrium, and that's supposed to be stable. And that was the diagram and the Paul Samuelson thing in the background. But when you think about it, like there's loads of people have pointed out the problem with this supply and demand diagram, but like a basic one is that what counts is the ratio of demand to supply, right? That's what, and that is in the quantum model, that's captured by this parameter here, which is like the imbalance in the market. So it's not what is supply, what is demand, it's the ratio. How much of unit, how much demand per unit of supply do you have? So you end up with like a different model, which actually fits the data very well and doesn't suffer from the problems of the classical theory. Related to that equation, so, which as I mentioned is kind of unique to the quantum thing, is that you're going to end up, so if I plot volatility, so again, that's kind of like the variability of this thing. And I calculate volatility, let's say, over a period of, let's say, 4 weeks. And then I look at how much the price changed over that period in percent. And then I look at the averages and I plot the relationship between volatility over a period and price change over that period. I end up with this shape, very steep shape. So big price changes are associated with big volatility, and it flattens out with time. And it flattens out inversely with the square root of time. So if I plot kind of a way to plot this in kind of a way to remove that dependence on time, this is to divide by the square root of time. So this is for the S&P 500 index. So I'm just empirically checking the results here, plotting volatility against that. You can see there's good agreement. There's the Dow Jones Industrial Average, good agreement. So the lines here for different periods of 1, 2, 4, and 8 weeks. And so what this means is that volatility and price change are related. Okay, so now, why does this matter in a, to our sort of financial system or whatever? Well, the reason is that volatility is kind of key to the way we think about risk, key to the way that we model risk, is key to the $quadrillion worth of derivatives that exist in the world economy. And so people may have heard of the Black-Scholes formula. So this is like 50 years old formula this year, and this is used to price options. So here an option is a security that grants the owner the right but not the obligation to buy or sell an asset for a set exercise price known as the strike at some specified date in the future. So for example, if you think a stock is going to go up in value over the next year, you could just buy a call option, which allows you to purchase it next year at the whatever price you select and sell immediately to make a profit. And these are very old things. They were sort of existed even in a sense back to the time of the ancient Greeks. And then the problem was that people didn't really know how to value these options. They didn't know, how to put a price on them exactly, and so the market was kind of held back. But then in 1973, the Black-Scholes model proved this theory, which was that the way they did it was to say that you could construct a risk-free portfolio by consisting of options and stocks and buying and selling continuously in order to create. So you make this risk-free portfolio, the return should equal the risk-free interest rate, and you get this formula kind of pops out at the end, which tells you the exact price of the option, and this won the Nobel Prize and led to a huge expansion in options trading, because it sort of changed the way we think about them, made it seem less like gambling and more like scientific risk management. And so the usual justification for the models in theory is satisfies this no arbitrage principle, but the proof involves numerous assumptions such as efficient markets, particular constant volatility, and so on. And in particular, that dynamic hedging argument assumes that you can constantly buy and sell securities and options to eliminate risk, but this ignores the bid-ask spread on those transactions, which is not a technical detail, but is a fundamental measure of uncertainty, which is related to the volatility, which is related to the growth rate. And in fact, it's kind of like actually the starting point for the quantum model. And really, the best way to think about the Black-Scholes model, if you kind of set aside that theoretical proof, it's really a statistical predictive model, which are based on two particular assumptions. One is that volatility does not depend on strike, and the other is that the growth rate equals the risk-free rate. And these are all related to this idea, of course, that markets are in balance and in equilibrium. But we can just sort of, the way to test this is just to go out and check it. So let's do two experiments. So one is that we're going to put in some artificial log normal data and calculate the Black-Scholes price of those options, which is the blue line, and then the actual payout, which is the dashed line, which is just behind the blue line there, and they're in perfect agreement. So the Black-Scholes model works perfectly for log normal data. As we know, data is not perfectly log normal. So what happens if you put in actual index data, like for the S&P 500? Well, then for that case, this quantum model with a smile, where the volatility depends on the strike price, gives a better fit. And in fact, this difference is about a factor square root of 2. There's also another shift here, which I'll mention in a second. And so to sort of check this result, we did an experiment. Larry Richards is a CTO at Gammon Capital hedge fund, and looked at over 25,000 straddles. And so again, this is the Black-Scholes model. This is the actual payouts, and there's that factor root 2 difference. And then what's interesting is you see the traders adjust the price to a degree, because they're using, what they do is they adjust the volatility which they input into the model. So it's sort of like they're kind of partially correcting for this effect, but the difference is still, instead of being 40%, it's more like 20%. So there's still a big difference. Okay, so really the message which just kind of wanted to get out of all of this is that the quantum model gives an accurate simulation of asset price behavior, which can be used to improve the pricing of options. And the model also has the advantage of being quantum native, so it can be easily implemented on quantum computers. So this is like a quantum circuit for doing quantum harmonic oscillators. So I think the message here is that, if you're like quantum computing company and you're looking for use cases in finance, and like the typical one is to develop a quantum model to run the Black-Scholes model. But really, it would be better to use the quantum circuit to run the quantum model, because first of all, it gives more accurate results, but also it's going to be native to the quantum computer, so it'll run more easily. Okay, so just to summarize, quantum is the language of money. It can be used to model money creation, economic decisions, financial transactions, stock markets, options, and so on. And applications include money creation, behavioral finance, such as mortgage defaults, stock market analysis, supply and demand, option pricing. It provides a framework for discussing topics such as money, power, subjectivity, and financial entanglement. all of which tend to be downplayed or ignored in mainstream economics. It predicts phenomena such as the square root law of price impact, the relationship between price change and volatility with implications for things like option pricing. Ada Lovelace wrote that the development of computers would exert an indirect and reciprocal influence on science itself. And I think a prediction would be that the increased adoption of quantum computers will similarly change the way we think about finance and the economy as a whole. So, so thank you very much for your attention. And there are some books on the subject I've written, and we also have a new journal which will be accepting submissions very soon, Quantum Economics and Finance, coming out with Sage Publications. Okay, thanks a lot.
Yeah, many thanks, David. That was an exciting journey through a lot of topics that, well, we all know from business school probably, and from economic studies. We have a couple of questions in the Q&A chat amongst quite a lot of very positive comments around the presentation, David. So very well received, and a lot of good positive reception already here. I want to start with an easy and fun question, because this is also a question that could have been asked by myself as someone studying at a business school or at multiple business schools. And there's like always this kind of sentiment as business school when it comes to economic theories, that there's like 80% of the students hate the math behind that. So, and now we're going quite math heavy here, right? And with quite a lot of interesting ideas. So the question I'm looking at here is just like simple, like why is in the business world quite often mathematics and economics being perceived as something too theoretical? Do you see some kind of a sentiment to that, or how's it from your work when you're working with companies? How do you see that?
Yeah, yes. I mean, mathematical models are they kind of have two sides to them. I mean, it's often said that they make something much clearer because you're forced to state your assumptions and, you know, name all your variables and so on. But also they can be used as a tool to totally obfuscate something, you know, because, and I think actually, I think this is really sort of true of mainstream economics actually, which is that their models are very, very complicated and almost impossible for anyone to kind of get to sort of criticize them and, you know, point out problems. And you have to be kind of an expert or someone who works in the field in order to do that. So I think that's definitely a problem. And the stuff that I've sort of presented here is kind of, I think is sort of at the tractable level, but it could easily sort of spin off into something where it's just, you know, yeah, you can demonstrate whatever you want. So I would sort of say though that the advantage really of like that quantum harmonic oscillator model that I showed, it doesn't, for me, the complexity of the model is really how many parameters and how many bells and whistles that you're adding to it. The thing about that model is that it has no extra bells and whistles. It actually, it doesn't involve any extra parameters. So in that, by that measure of mathematical simplicity is actually much more comprehensible than a more complicated model, which tries to do something else. But I think like the quantum, we call it the quantum ideas going into economics, they can work on different levels. And so one thing is that there's the mathematical side, but there's also what it draws our attention to, really. So one of the things about the quantum stuff, like I showed how it applies to the creation of money, all that stuff about debt and credit is something that doesn't really fit with the mainstream model, but it's something that's totally obvious in a way, you know. So for example, how the creation of money by banks affects is correlated with house price index. So I think there's like different levels where you can kind of come in, or the way like our decisions about, you know, defaulting on a mortgage, it's not totally a rational thing. It's affected by subjective things. So you can understand it on that level, on the sort of psychology level, on the money creation sort of side. You don't always, it's like the ideas are changing the way that we think about the economy, just as mechanistic law of supply and demand has changed the way, has decided how people think about the economy. You know, it's like so much of the discussion about economics is sort of like a Victorian kind of mindset, you know, really, where you kind of talk about, oh yeah, we got a new equilibrium of the supply and demand and stuff, and not enough so so I think part of the advantage of this stuff is that it will trigger sort of like as Ada Lovelace said, it's just going to like trigger like new ways of looking at things.
Yeah, and I think like also there were a couple of years ago, especially in Germany, but I think it was like a little bit like a global trend where a lot of like books came to the market that like tried to explain a lot of economic theories in like really simple words, or like with almost childish examples, and people all of a sudden all became like super interested in economics in general, right? Without like seeing, hey, there's a little bit more complexity than like these simple examples. And like also quite a lot of books on how to deal with data have been like quite popular, right? I think like this overall sentiment towards math, and like this seeking the easy answers always seems to be a little bit too simple from where we are, right? Because a lot of things can't be simply explained, and a lot of those things probably can't even be explained whatsoever. And looking at even further when we're talking about technologies, I mean, you touched up on basically two, even directly, right? One is something like the cryptocurrencies and the blockchain technologies in the very beginning of the presentation, and like a lot of quantum ideas behind that, and they're quite seldomly being taught in like subjects where they probably could create benefit, right? They're quite often put into like applied computer science, right? Blockchain especially is quite often buried in like a DLT sub course in ICT. Quantum is being buried in physics. And then like that's what I really liked about the presentation as well, right? So like, hey, there's a lot of like sentiment also not to do these kind of things, but I think in the world that we're living now, everything is becoming so complex, where can really benefit from taking ideas of different subjects and bringing them onto the table is quite meaningful. And that brings me also to the next question that we have in the chat from Elizabeth. And her question is actually, and I really like this question, is that the whole part of quantum economics is not really visible or seems to be like really emergent from a field perspective. How do you see other economists applying, on the one hand side, these principles, and on the other side, what's the overall sentiment? So how do you see that as, or are people in this field more and more adapting to these kind of schools or thinking ideas, or is there still like a lot of resistance towards these topics? How do you see like the overall industry from an economics perspective?
So how are economists reacting to sort of in universities and so on? Well, I think the answer to that is very simple. It's not on the radar really, at the moment, but I think it's changing. So for example, this journal that I mentioned is the first journal in the area, and I think actually like a really interesting question to ask is why it's taken so long, because there's because quantum ideas have been around, for over 100 years. And so they haven't really been, but there are no journals about quantum applications to things like social sciences at all, or psychology or the economy or finance. So there's two possibilities. One is that the models do not work, right? And there's no point, so, or the other one is that they do work and there is a point, but they're being kind of like held, they're sort of being held back for some other reason. And so obviously I think it's the latter, because I think you can kind of go out and demonstrate that actually objectively these things do work. It is like the right framework for describing lots of things. But so why are they not on the radar of, like, if you went out and asked economists, I don't think they would have really heard of this stuff. And I think it's because there's a lot of, I mean, actually, I guess to be honest, I think the relationship with these quantum ideas in physics is tricky, because on the one hand, because it's sort of like we just associate them so strongly with subatomic particles and so on, it's very hard to justify the leap to something which obviously has nothing to do with that, So, but I think that's sort of like an interesting question. But I think just to kind of sum up, basically, these ideas are only starting to get diffused. But there is one of those things where things are kind of growing at the exponential rate. So basically, there's about twice as many publications now this year as there were 2 or 3 years ago, and that's going to keep going, I think, for a while. And so if you ask me again in 4 years, I might have a totally different answer.
Awesome. I just put a follow-up question here, which we have actually from Ludmilla, which is going directly into the same direction, right? I mean, you're talking about like this awareness for the topic, that it's not really in the spotlight, right? That there's like not this topic of choice probably for many to position themselves right now, but probably, as I said, right, there's a lot of development. But on the other side of the spectrum, right, if you have people or if you meet people in this field that know about it and that see this topic, is there more like are they more resistant to that? Or is it like, oh no, we should stick more with the traditional economics approaches, or is there openness? Are people like fascinated? So how do you see this from the ones that are aware of that?
I think the ones who are aware of it, it's sort of a strange field, because what I find is that if you kind of talk to like most people, they won't really pick up on it. But what you do is you find like people individually, kind of by themselves, they sort of come to the conclusion that this might be the right idea, you know, and so they're starting to kind of come together, and we're sort of starting to solidify things a bit. And I think one thing that actually is changing the debate, and this relates to like, you know, the earlier answer as well, is that suddenly quantum computing is kind of becoming a thing. And so all of like the bigger banks and, you know, and lots of big companies have little quantum computing groups in them now. And so if you take a big bank like, you know, RBS or whatever, or Goldman Sachs, or, you know, Morgan Stanley or whatever, you know, they will have people who are interested in quantum computing. And the one audience that I would say is a bit more receptive to this kind of work actually is people who work in finance. And part of it is because they kind of have like a mathy sort of background or whatever, they're more kind of into it, but also because they see that quantum computing is becoming a thing in their field. And so they want to start thinking using this different logic. So that's really acting as an accelerator at the moment. So again, you know, like at the moment, I think it's kind of, things are going to change a lot, you know, over the next few years.
Yeah, fantastic. With respect to the time and yeah, like all the topics that we already covered, I have just one last question for you, David. And while you were answering that, for the ones that are interested, I'm just like putting up the QR code that you hopefully can see now. If you're interested to learn more about the master's program or to join our future masterclass series here, feel free to scan this code to stay in the loop. And for you, David, the last question is, are the slides available for download, or are you sharing any information on that end?
I don't have these slides available at the moment. However, I do have, a lot of them are pulled out of, I have a YouTube channel on quantum economics and video. So it's got like about, you know, 12 or 15 different lectures pieced together. And yeah, I'll probably be making a version of these publicly available once I can, but it's not out there yet.
Yeah. And I can only recommend to everybody, and David has great resources online, so you can follow along his journey and the works he's doing. So that's one call of action here. There was just now coming in a follow-up question. If you're open for people to connect with you on LinkedIn, I guess that's a yes. So that's probably also a good way.
Yes, and if there are any further questions which I didn't have time to answer, please contact me through LinkedIn.
Fantastic. Thank you so much for everybody that was participating here, and hope to see you with the next classes. David, thank you so much for sharing your insight and your story. Much appreciated, very insightful, and I wish you all a wonderful rest of the day wherever you are on this planet, and I see you in the next class of this Quantum Masterclass series. Thank you so much. Have a good day. Bye-bye.
Bye.